Okay, so today in this webinar, we will discuss the capabilities of the RF option in PADS Professional. PADS Professional Suite incorporates the technology of Mentor's high-end layout software, Expedition, into the PADS design flow. This adds to the PADS flow capabilities like correct by construction methodology, hierarchical planning and placement, sketch router, and advanced constraint-driven routing that are familiar to Expedition users. One of the advanced options available with the PADS Professional is FPGA-PCB co-design. This software automates the optimization of the FPGA and PCB integration. It understands the architectural features of your specific FPGA and facilitates forward and backward changes to the FPGA and the PCB pin designations to improve the routability of the design. PADS Professional recently introduced a rigid flex option that allows multiple board stack-ups and understands flex-specific layer types such as cover layer, adhesive, and stiffener. It provides full control over where the bends can display and check the flex board in 3D. It also has an RF design option, which we will cover in this webinar, providing schematic, layout, and manufacturing integration. This option understands that RF circuits are not dumb copper and allows the design of RF shapes parametrically in either the schematic or PCB. It can provide dynamic integration with the RF simulation tools such as Keysight Agilent ADS and AWR Microwave Office. And you can synchronize the PCB and RF libraries between PADS Professional and these simulation tools. You can convert any imported copper into an intelligent RF shape, manage the connectivity of these RF structures, and therefore generate manufacturing data based on an intelligent RF design. Integrated RF layout functionality provides a designer with the capability to create intelligent RF structures natively within the tool set. Data can be created by drawing the structures within PCB layout or by importing data from RF point tools using VXF, Gerber, or other data formats. A common problem with the importing of RF structures is the handling of connectivity and manufacturing data. The RF layout functionality allows you to convert any created or imported data to intelligent RF structures where both connectivity and manufacturing data is easily understood. Let's take a quick look at the RF capabilities and how copper data can be easily converted into an RF structure. Here we are showing the conversion of an imported filter into an intelligent RF structure. First, convert the non-conductive polygons into a conductive shape. This is done using the Draw Properties dialog. With the conductive polygons selected, they can then be converted into an RF shape. Now connection points can be added, also referred to as nodes. This is done from the right mouse button menu while the RF structure is still selected. For this example, the nodes are connected to the same net, but nodes can be connected to different nets with correct DRC handling. It is now possible to move the RF structure as a single entity. To connect it, simply move it over a node or component pin with the same net and it will automatically snap into place. To complete the connection of a Mander or RF trace, an RF trace can be added to connect the other end of the filter. The filter is now connected and DRC will correctly handle the connectivity, and the manufacturing outputs will also understand that the imported filter is now an integral part of the RF circuitry. As you saw in the video, the RF option has a special RF-aware routing called meanders. The RF layout provides the designer the capability to route and manage RF signals fast and accurately. The RF meander is a dedicated object type and is a highly configurable object that allows the user to seamlessly route and manage complex signals for RF design. As I mentioned earlier, clearance rules can be set up for RF elements to check spacing on same and also adjacent layers. The meander uses the same sophisticated clearance models as all other RF elements, allowing the user to control clearances on the same and adjacent layers as meander is inserted. To optimize the performance of the RF circuitry, there is also a powerful tools set available for inserting ground vias around RF signals. So let's take a quick look at RF layout and the meander capabilities. The meander object is highly configurable and allows the user to taper up and down on the fly. The meander automatically adjusts its width up or down as it connects to other RF elements in the design. The meander can be routed on any layer, and to transition between layers, you simply double-click and continue with the meander on the other layer. If you change your mind while writing the meander, you can backspace any number of segments, even back to the vias, and take another path to the target. The meander supports a variety of object types, such as miter, radius, and free radius. The bend type can be changed at any time during the meander command and can be mixed within the same meander object. When using miter bends, the miter percentage is controlled from the user-defined table. This allows the miter percentage to automatically adjust itself based on the angle the meander is inserted, thus creating the optimal miter on the fly based on your preferences. Observe the miter percentage field while this miter is being inserted, and notice that it updates on the fly as the angle changes. To make connections as smooth as possible, the meander has the option to automatically have a smooth path between connection points. With the smooth termination option enabled, all you need to do is move the cursor over a target pin, and the optimal S-shaped meander is inserted automatically. To insert a meander with a fixed length, you can use the serpentine option. This will insert a serpentine-shaped meander based on the desired length. The ghost shape of the meander updates on the fly as you enter the parameters. There are several ways to modify existing meanders. You can modify individual segments of the meander or the meander as a whole based on the selection. To modify the width of individual segments, simply double-click the meander segment to invoke the parameters dialog box. Use this dialog box to edit the start or end width to create tapered segments or to change the width of entire segments. You can also change the width of multiple segments at the same time by window selecting the multiple segments. To interactively edit the meander, invoke the Edit Meander command and move the segments as you like. When moving segments over each other, the command will snap them into place and remove redundant segments. The Edit command also provides options to lock bends during the edit operation to allow seamless editing of meanders at arbitrary angles. The meander uses the same clearance handling as all other RF elements. This means that you can define clearances that will keep traces and other design objects away from the circuitry, not only on the layer that the meander is inserted, but also on adjacent layers. While adding this meander, you can see how the dynamic plane data is updated when I added each segment. I will now set a Z-axis in clearance for the layer below the meander. This is to keep traces, planes, and vias away by 40 mils. When routing away from this component, you will notice that the trace is obviously not allowed to cross the meander on the same layer. Now, if I add a via and plow right on the layer below the meander, you will also see that the trace is still not allowed within 40 mil. This is a very efficient way of making sure that the traces do not disturb the circuit performance and are always kept at a safe distance from the RF circuit. A common task when optimizing the performance of an RF circuitry is to add ground vias around the RF signals. And in this example, I demonstrate both stitch contour and stitch shape methodologies. As the name indicates, a stitch contour is used for adding vias along the contour of a design object. You can select a mixture of objects. In this demonstration, I am selecting a meander and a few elements from the mixer circuitry. 2 rows or vias are then connected to ground around the selected objects. One really useful option when using stitch vias is to group the vias within the object. This will allow you to move all the vias together with the object as a single unit. You can still move the individual vias that are in the group. If you need to flood the whole plane with vias, you can do this with the stitch shape option. Simply select the plane shape, set up your parameters, and apply. The plane will be flooded with vias within a few seconds. Earlier, I said that you can import copper shapes and convert them to RF components. They could be elements that were developed in an analysis tool, such as AFSSS, Microwave Office, CST, or some other simulator. Once in PADS Professional, they are easily converted to a real RF component, as we have seen. A schematic symbol can then be automatically created and used in Designer to establish the connectivity of the component. The RF layout functionality is designed to specifically understand the RF domain elements to provide the use with a powerful and comprehensive tool set for integrated RF design, utilizing an equivalent library created from RF point tools. Schematic integration and layout verification is achieved through tight integration with those leading RF point tools. RF design elements are understood as native design objects, with support for many RF options, including parametric-driven RF elements and intelligent RF circuit placement. So let's take a look at the RF layout's parametric shapes and placement capability. During the design creation, you can place the RF models using Databook, similar to how you place any other schematic symbols. The RF models have their parametric parameters included in the library and are available to be placed as soon as they are added to your library. Finding the correct symbols is very straightforward, since the name of the symbol matches the name of the third-party RF tool. You can either browse or search for the symbol using Databook. After placement, the RF symbol's parameters can be modified in the schematic or in layout. Native support for all common variables and most expressions from the third-party tools, and also mathematical operators in the variable names, makes it possible to use complex expressions to meet your design needs. The variables are used to drive the physical size of the elements, as in the example where the length parameter on the microstrip is driven by a variable. To aid in the placement and movement of RF circuitry during PCB layout, it's possible to create groups in the schematic, and subgroups can be used to split the groups into more manageable pieces. In this demonstration, we will divide the LNA by its input, output, and amplifier stage. With the grouping set up, now let's take a look at the placement process in PCB layout. To efficiently lay out the RF circuit, several ways are supported to place the RF elements. One way is to use the planning group concept, which is supported in the RF design process. It will let you plan for the RF circuitry early in the design process before the circuitry is fully optimized or even complete. RF layout provides full auto arrangement of the planning bubble, but can also be limited to subgroups and individually selected objects. Within the circuitry, carefully grouped, it is now easy to identify and move different pieces of the circuitry independently. Moving and connecting shapes is fast and easy, as the cursor will always attach to the pin. Simply drag it close to where the shapes are and release it, and it will snap into place. A subset can be moved and connected to other shapes as a unit, and by stepping through the non-connected pins, you have full control over which end to connect. To automatically arrange a subset of the circuitry, simply select the shapes you want to arrange and define the seed on the fly. Changing parameters on the RF shapes within PCB layout is easy. Simply double-click on any RF shape, and the RF parameters dialog displays the editable parameters of the selected shape. Edit the parameters using absolute values or type expressions directly into the form. Parameters can be modified on multiple shapes in one operation, and the dialog will only display parameters that are common among the selected shapes. If you are defining the physical size with variables, equations will help you find the available variables for the selected elements. Variables can also be modified or added using the Variables and Equations dialog box, invoked from within the Component Explorer. Variables added in layout are back-annotated to the schematic, ensuring that the schematic and layout are always in sync. Typing new values directly into the form will create complex expressions using the equation editor, which will list all of the available variables for the currently selected group. Toggle between the expression and the actual value to ensure that the equation can be resolved. Then modify the variable to instantly update all RF shapes using this variable. This will allow you to control the physical size of entire circuits, making it easier to manage complex RF circuitry. The results in a best practice flow where several RF designers or RF teams can work in parallel, creating optimized RF components to use in the final design. This allows the design to be done in the optimal tool for the particular task. This also allows best practice of verifying each RF element and the design as a whole. This task is simplified with the tight integration of the tools that we have been showing you here. For example, integration to Keysight ADS simplifies the process of tuning and optimization. The design cycle can be significantly shortened with this bidirectional tuning flow for RF interconnects. This integration allows the matching of libraries between Keysight ADS and the designer layout environment. Designs can be done in either flow and then transferred to the other flow with a bidirectional interface, resulting in a faster and safer design process and fostering efficient team collaboration. The integration with Microwave Office allows the design to be done there, simulated, and then transferred to the designer's layout environment in PADS Professional. Design could also be done directly in PADS Professional and the copper shape transferred to Microwave Office for simulation and verification. The following video demonstrates integration with Microwave Office. So as you can see here, we have DX Designer on the left-hand side, and we have the Microwave Office schematic on the right-hand side. Because the libraries have been synchronized, it's possible to transfer the design that was done in Microwave Office on the left into DX Designer. And you can see here that we're able to import the design as it was transferred from Microwave Office. And now it's expressed in the DX Designer environment, as you can see on the left-hand side. It's possible for me to make parametric changes in this design, either on the Microwave Office or the DX Designer side when I'm working with the elements on this particular design. So this is showing you the integration of the DX Designer schematic with the Microwave Office schematic, able to reproduce the design in Designer that was done in Office. So you can see here we're making modifications and then importing those modifications into the design. I'm placing symbols in the design to be able to take the elements that we created in Microwave Office and then integrate them into a full design flow in Designer, which then can be transferred to PADS Professional. You can see here we're creating the groups that we had shown earlier in the process. So then when we go over to PADS Professional layout, that same group is available to you. So you can see here that I'm actually extracting that placement group and then going to extract the individual elements of that. On the right-hand side, you can see the layout copper as it was created. And now what I'm going to do is I'm going to extract the data on the left-hand side, which is in PADS Professional, and you'll see that that same structure is created now in PADS Professional. So this would have allowed me to do my simulation over in Microwave Office to verify the elements and then easily transfer that design, intelligent design, back into the PADS Professional environment. But let's say we needed to make some changes. So what we're going to do here is we're actually going to change the design by changing some of the parameters in the Microwave Office schematic and then taking that and then using it to edit the copper. So you can see here we're making changes. We're adding length onto the copper, and we're going to also then copy those stitching vias and add the stitching vias into the design. Now what you want to do now is export that particular design element over back into PADS Professional. So you can see that's what we're accomplishing now. We're picking all those elements and importing them, and you can see now that I've been able to reproduce in PADS Professional the same copper structure that I was using before. The changes to the schematic can then be made to the schematic and updated. So in summary, we've been able to emphasize the capabilities of designing RF in parallel rather than serial by being able to use multiple tools and integrate those tools together. This fosters efficient team collaboration and concurrent design. RF library is managed in one place for less effort and less risk, and then transferred to the other tools. This means reduced risk because you were able to check out the designs more accurately, to be able to take advantage of the concept that we talk about of virtual prototyping, being able to build it in software before you build it in hardware. You also have the advantage of having a solid business partner in Mentor Graphics. It is the largest supplier of EDA design software in the world, and therefore its large market share enables significant investments in new technology, able to help you as you continue along the design process.